Hello everyone. Today we'll be discussing about the Bellman-Ford algorithm. Previously we had discussed about the Dijkstra's algorithm, right? So now we'll discuss about the Bellman-Ford algorithm. So basically let's go step by step. Bellman-Ford algorithm, basically it is used to find the shortest path distance. So here it is used to find the shortest path from the single source node to all other nodes, right? So from single source node to this is nothing but single source node to all other nodes, right? So it is used to find the shortest path. So just for the example sake, I'm doing this one in a graph that may have negative edge weight as well. So it can have the negative edge weight as well here. So this will be very handy when we have the negative edge weight basically. So this is the reason we'll be making use of the Bellman-Ford algorithm. So what are the steps? First thing, let's come to the second step. So first what we will do, we will initialize the distance from the start node. So we'll initialize the distance from the start node. Suppose this is start node, we'll initialize the distance from here, the start node. And from the start node to all other nodes as infinity. So initially we will initialize from the start node to all other nodes as infinity, right? So except for the start node itself, which is basically 0. We know that one, right? So next, so this will be the second step. Next, what we will do, we will iteratively relax all edges to v minus 1, this one, v minus 1 times. We will iteratively, this one, relax all the edges up to v minus 1 times, right? So where we know that v is nothing but the number of vertices, and finally we will check for the negative weight cycles. So in fourth step, what we will do, after iteratively relaxing all the edges up to v minus 1 times, we will finally check for negative weight cycles. So we will check for negative weight cycles here. So if a shorter path is found after v minus 1 iterations, then it means that graph contains a negative weight cycle. So if the shortest path, we find the shortest path after v minus 1 this one iterations, then it means that there exists negative weight cycle. So we have the negative weight cycle if we have found the shortest path after v minus 1 iterations, right? So then finally this is the step. So basically we have got the answer here, right? So this is it for this algorithm. So this is basically slower than the Dijkstra's algorithm. Previously we had discussed about the Dijkstra's algorithm, right? So but it works for graph with negative weights unlike Dijkstra. So Dijkstra doesn't work for the this one, the graph with negative weights, but the Bellman-Ford algorithm works for the graph with negative weights. This one you have to keep in mind. This will be very handy, as I have said, if we have the graph with the negative weights. So we can make use of the Bellman-Ford algorithm. So first what we will do, let's try implementing this one in the code. Then we'll understand this one with the example. And finally, let's discuss the time complexity and the space complexity. So first step is, let me write the function here. Function Bellman-Ford. So this one, let me consider the parameter edges v as well as start. So I hope this is clear. First step is, let's initialize the, as we had discussed, we will initialize the distance array with infinity for all the vertices. So this will be distances equals new array of v, and also we will fill this one with infinity. Finally, we will initialize the distance to the start node, that is nothing but 0. Distance of start node, nothing but I can consider this one here like this, right? Start, you'll initialize this one to 0. Then let's start with the step 2. So we have to relax all the edges up to the v minus 1 times, right? So after initialization, let's start the iteration. This will be, let I equals 1, I less than b, I less plus. So we are repeating it v minus 1 times. So next step is, for each edge in the graph, we will check if the shorter path is found or not. That's what we have to do, right? So for each edge in the graph, we will check if the shorter path is found or not. Again, here, right? So within the array, I'll just consider u, v as well as weight, right? So weight of all the nodes, so all the edges, right? We have to for each edge in the graph we have to consider, right? So of all the edges. So next, we will check if the shorter path is found or not. For this, I'll just write the if condition. If distances of u is not equal to infinity, then and also distances of u plus weight, if it is less than distances of v, this one, what we will do here, for this we will update the distance if shorter path is found finally. So this one will be distances of v here, distances of u plus we can consider in this way weight. So nothing but we are updating the distance if the shorter path is found. So final step was we have to check for the negative weight cycle. So as we had discussed, we will go for each edge again. Nothing but let's start the iteration in this way. So it will be, sorry, where am I writing this one? Sorry, just give me a second here. So after this I have to consider, right? So we will we have to check for the negative weight cycle. Nothing but for each edge again we have to consider, right? So I'll just make use of the for loop here. Let and let me consider weight of edges. So for each edge again, we'll consider if the shorter path is still found, then there is a negative cycle, right? So then we have found the negative cycle. So I can just make use of the if condition and I can write here, if distances of u, if it is not equal to infinity, then and distances of u plus, here I can consider weight less than distances of v. Yeah, then what I can give here, let's make use of the error. Nothing but we have detected the negative negative cycle, sorry. So here it will be, let me consider something like throw new error, and let me give here graph contains negative weight cycle. So here I hope this is clear. Finally, after this step, we will return the final distance array with the shortest path. Nothing but we have made use of the variable name distances, right? So I'll just return the distances over here. So this is it for the code. Let's consider, let's try with the example. So I have just considered this one, the same example that I have took for Digitstar previous video. I'll be taking the same example, the edges. So here 017, 029 to 459 finally. Let's specify the number of vertices. Let me consider, we have the number of vertices 6, right? 0, 1, 2, 3, 4, 5, 6 here. So number of vertices we have 6, and let me consider start node and initialize this one to 0. So here finally let me make use of try catch here. Sorry, what did I do here? So yeah, try here, what I'll do, I'll just consider the distances, this one variable. Let me call the Bellman-Ford function here with the parameter edges v, and one more thing what I took, start node we have to take here, right? So we are just calling the algorithm over here. After calling the algorithm, we have to print this one, right? So I'll just make use of the console log and let me give here, within the backticks, I'll just give here Bellman-Ford shortest distances, nothing but within this one, sorry, this has to be distances, not the capital one, right? So the output that we need to get is here 0, 7, 9, 20, 20 and 11. The previous shortest path we have got for this one distress algorithm, if you have followed the previous video, the same output that we need to get. But the thing is here, even we can find the shortest path for the even if the graph contains negative weight cycle as well. That is the reason we'll be mainly using the Bellman-Ford algorithm for this one. We have to keep in mind. So let me just make use of this one error here. So console log of here considered E, right? I'll just give error dot message. So let me, so if the negative cycle is detected, then we will log the error here. So I hope this one is clear, right? So I'll just come here, let me run this one. So you can clearly see here Bellman-Ford shortest distance is 0, 7, 9, 20, this one 11, right? So we are getting this one correctly. So everything works properly here. So what will be the time complexity and the space complexity here? The time complexity would be big O of, so I'll just give here, the time complexity would be big O of V plus E. And what will be the space complexity? The space complexity would be big O of V. So here the time complexity is big O of V, sorry, this has to be big of V into E, not V plus E. So it is V into E, where V, we know that it is the number of vertices and E is nothing but the number of edges. V is nothing but N, if we have considered N, it is nothing but number of nodes, and E is nothing but the number of edges. So space complexity would be big of V. Because we are storing the distances, right? That is the reason we'll get big of V or big of N. So I hope this. So yeah, this is it. Thanks for watching, guys.